Welcome back to Element 14 Presents. I'm Clem and this is a desk calculator or an adding machine. I've used this back in the day at my old job and I loved it, but this is big, bulky and it needs AC power to work. So could I make my own version of an adding machine, a desk calculator, fully open source, battery powered? Could be an interesting project. Let's get started. I think there should be an open source version of everything, including desk calculators. I love machines like this because they have buttons like a keyboard. They are super fast to type on. They get you exactly what you need and they don't slide around on the desk like a small little school calculator. So you can punch in numbers like crazy and get people the stuff that you need, because that's what I did for about 10 years. So now I have a different use for these, and I basically use them as a four-banger. So the basic four operations that I do with a calculator. I want this to be open source. I still want it to be super sturdy and have the perfect buttons for fast data entry, but I also want this to be a lot smaller and battery powered. As it is tradition with these projects, we have to make a schematic and a PCB. But before we can get to that part, we have to select our components. Specifically, we have to make sure that they all work with the voltages and power levels that we intend to use. So I want this thing to just run out of batteries. AA's or AA's, whatever I can fit in the case basically. So all the components in there have to be usable at 3 volts and should be usable at a bit below, because batteries drain over time and then the voltage get a bit lower. And I still want to get the most out of the batteries and not have them shut off just because they are at 2.9 or something. As the brain of my project, you could suspect that I use an ESP32, which would be totally overpowered. I could use an 80 mega 32HP like on the old Arduino Uno, which would be kinda overpowered and maybe a bit too big. But what I want to actually use is a modern 8-bit CPU that has the exact right features and the exact right number of pins for my project. So I'm choosing an ATtiny3226. Why on earth just that specific chip? So the reason for my selection is simple. It has the exact right number of I/O that I need. So I need to have a full button matrix. I need 16 keys, but I use them in a grid, in a keypad matrix, which is constructed with diodes, so I can use multiple buttons at the same time. This is called N-key rollover. And for that, I basically need 4 by 5 rows, which allow me to use just 9 pins for that. And the rest of the pins are taken up for UPDI programming and to interface with the display, which is HD44780 compatible. And we have to be very particular about that display because it also has to run at 3 volts, and most of them run either at 5 volts or 3.3 volts, which is not the same. Totally not coincidentally, the ATtiny3226 also runs at 3 volts, but it can go from 1.8 volt to 5.5 volts. So I have a broad range of voltages where I can use that device. And why that specific chip, apart from the pin number? Size of the flash memory. I've used ATtinys before in numerous projects you have seen on the show. The trouble with a lot of ATtiny projects was that I've used the most minimal chip for the job, which is cost effective, but it also limits you. In some projects this was really cool to basically challenge myself to optimize my code, my layout and stuff. So it actually works with such a tiny chip. But in this case, I know that if I need to have some libraries in there that would help me code this thing a lot easier, then I would have to provide enough space for it. And by choosing that particular chip, I have more than enough space so I can fit the libraries that I want to use. The Adafruit keypad library for the matrix keypad, of course, and I want to have the LCD, the liquid crystal library, both directly imported from the Arduino Uno IDE. Arduino IDE, because I'm programming this ATtiny board that I construct also with Arduino. So you can play along at home and make your own version easily. The buttons that I use are just normal key switches from mechanical keyboards. These are Cherry MX, the good ones. You can get them in a lot of flavors. These are just normal linear ones. I usually prefer the clicky ones. These were in stock and were pretty cheap, so I got those. The nice thing about building your own calculator is, of course, you can decide which switches you want and how they should feel. You can tune that to your liking. And also the display, I've chosen a white on blue variant by 4Data that runs on 3 volts specifically, for the very important reason that it was available and did find it first. But there's also, I think, a yellow on green one that has a lot of retro character. So the choice is yours. They all basically are very good readable. Make sure to get one with a backlight, because even if you don't need the backlight, you can deactivate it. Speaking of deactivated, we need to have a PCB to connect all our components, so let's hop on over to KiCad and check out the PCB. Welcome to my computer and KiCad. So we start with the most important thing, this here. That is the keyboard layout that I want to reproduce. So I have a 4-banger, which means I have the 4 basic arithmetic functions: plus, minus, divide, and multiply. I have a decimal point. I have a delete function, which makes sure that if I mistype, I can correct mistakes. I can clear everything that is currently in there. I can control the backlight, and this is for a soft power function that I might want to implement. So how do I do this actually? Well, first I have to have a matrix of buttons. Each of these buttons has a corresponding diode. This is needed so we have true N-key rollover. This is the way a keyboard does it. If you want to know more about how keyboard and matrix scanning and stuff works, I have a big episode about building a BLE keyboard from scratch that works exactly like that. And I've also did an episode about Charlieplexing for keyboards and whatever. So you might want to check those out to really understand how they work. But basically, we only need 1, 2, 3, 4, like 5 by 4 pins to control all these buttons, to read them all individually, and we can even detect when multiples have been pressed at once without any ghost presses, thanks to diodes. This is the connector for my LCD. I'm using a 4Data. This is the model number. Important, this one runs on 3 volt. Most of them don't, so check that before buying one. We just need a few pins. RS, RW, and enable are important, and then we need the upper bits, so 7, 6, 5, and 4. We can leave out the other ones that just saves pins. Doesn't matter if you're just using the standard ASCII set. We're just using numbers, so no need for special characters. And this here makes all the thing tick. So this is an ATtiny3226. This is programmed via UPDI, as you can see on this pin here. It's broken out on a little header that corresponds with a UPDI program. There is no standard pinout for that. Look at your programmer, which can be a simple homemade thing made from an Arduino Nano, for example, or from a serial to TTL translation device, something like that, or you get a dedicated UPDI programmer. This little chip has the exact, and I mean the exact number of pins that we need. Not one more, not one less. So this pinout corresponds to the numbers in the Arduino IDE. How did I get those? I've looked at the ATmega core by Spencer Conley. I think it's Dr. Azzy on the internet. And basically there is a little picture where I can see what all these PA and PB ports correspond to in Arduino numbers. Fun fact, across series, these are all numbered the same, so you can use multiple versions of the same chip, like variants with different amounts of flash, and they are still pin compatible. So if you want to like downsize the cost of your project once you make more of one, then you can just use the smaller chip if your code still fits and don't have to change anything about the PCB. Really like that about the ATtinys. This is my backlight control circuit to activate the backlight with a transistor. And this is just a simple power switch, and we're running this on 2 AAA batteries. Here's the PCB and some notable facts about it. You can see this is where the AAA batteries fit. So they go directly into a holder onto the upper side of the PCB. And above this will be the screen. So the screen is just connected with this ribbon connector here. You can solder a full ribbon to that, or you can just use individual wires to connect only the pins that you need. In reality, you just need like the first 6 and the last 6 on this connector. But you may just want to solder all of them. This is the power connector, where you can just solder in a switch and then position that in your case as you please. Here is the programming header. This is where the chip goes. And these are all the diodes. In the schematic, you've seen all the diodes directly near the switches, which is a way that you can do it. I did it in the BLE keyboard episode, but now that I've learned and I've refined my ways, I deliberately routed this in a way so that all these diodes are here next to the chip. I can easily populate them. I can easily check their orientation. And you see how all these line up perfectly with the pins of the chip and with the rows and columns on the board. That's like really nice routing. I'm kind of proud of that because it's like super clean. There's very little on the backside, just a few connections here. But it's not like a mess of jumbled wires. No, it's very well organized. You can easily trace out which pin corresponds to which diode, to which switch, and also the numbering of these corresponds to each other, which is very handy for debugging. So let's send this board to Eisler and get it made and populated. We have to go from our schematic to a fully fledged PCB. Thanks to Eisler for sponsoring the PCBs for this and many other projects. We now have a base where we can solder all the components to. Just in this corner there are SMD components. I will reflow solder them, and the rest will get soldered classically by hand. For the case, I want to get a bit creative, and I also want it to be super sturdy. So what I do is I got this. This is a die-cast aluminum box by Multicom Pro, and I only use the lid, which means this thing is ready for other projects. So the lid is basically a die-cast aluminum piece. It's very sturdy, it's very heavy, which is logically for a piece of metal, and I'm constructing my PCB to perfectly fit inside this housing, and then I construct a 3D printed shell that goes on top, holds the screen, and gives us access to the buttons. Also, of course, we have to 3D print the keycaps ourselves to have the right layout. So, die-cast box, PCB will fit right in, and because these are conductive, we need to have a spacer on the bottom so all our contact pads won't short out on the die-cast aluminum. So this should give us the most solid base for a case you can wish for. I've constructed the upper portions of the case in FreeCAD, and then I 3D printed them with PETG by Multicom Pro again. So this is actually a Multicom case, by the way. So we have our bottom shell in aluminum, and then we have this 3D printed upper part and 3D printed keycaps. They hold in perfectly well. This PCB is not screwed in, it's just fitting so well inside the case that it just stays in there. And the Screen is connected via a few cables directly to the PCB. That's a hand solder job, and it's very easy to mess that up because I had to repair multiple cables. Yeah, at the moment this pretty much does nothing. That is because we need to put some code on there. So let's check out the code.
Welcome to the Arduino IDE. It's time for the code. We just go over that in its main aspect, so I don't bore you. So we use a few libraries. We use the Adafruit keypad library to have an easier time scanning all the rows and columns. We define this like so, and we also define our keypad. This is almost graphical. Keep in mind that we name these just with a single letter because we actually use the ASCII code of these letters to identify the buttons, so don't write stuff like BLE or something or backlight. What you need is just a single letter to identify these. We have our liquid crystal display library. That is important because we have to fit all the stuff in one tiny little chip. If you use a small ATtiny, that might not fit. That's why I use a bigger one. Even though like the whole code has about a bit above 8 kilobytes of RAM, 8 kilobytes of flash, takes up 8 kilobytes of flash. I have 32 now, so I still have a lot of space on there. Could implement a few more gimmicks, but if I would use like something like an 8K chip, then this wouldn't fit, and I would have to like bit bang all the stuff, and I don't want to do that. It's also easier to understand because we can just print on the screen with just set the cursor to a specific position on the screen. This is a 20 by 4 LCD, which means it has 4 rows and 20 positions, and we can just address these. And first one is the position within a row, and the second one is the number of the row. And conveniently for this screen, this is not the same for everything. These are numbered 0, 1, 2, 3, and they are sequential. But if you just keep on writing, in the first row, it will then continue on the third row. This is the way it's actually addressed in memory, and this form of addressing is taken care of by the LCD library. You can see how this makes things a lot simpler. Yeah, we basically use the library to always look for button presses, and in case there is an event, then we read whatever that is, handle that key press, process all the stuff. This is like a bit more complicated code. We perform our calculations according to whatever thing has been pressed and displayed on the display. That's it. That's what a calculator does. It has limitations. We will get to that in the demo.
With the code ready, we have to now finish him and flash this on the device with UPDI. We have made a UPDI programmer in a previous episode, so if you want to make one yourself, you can. All you need is basically an Arduino Nano, a resistor, and a few wires. Oh, and some code. But you can also make them from serial to TTL converters pretty easily. I think this is kind of a really neat way to flash small chips, especially if your project doesn't have or need a USB port. So if we turn this on now, it lives. And before demonstrating my little homemade calculator, also I want to show you that the backside is laser engraved with 00 calculator, which 00 is the way I call all my basic versions of things that should be open source. A very basic open source desk calculator by Mayamix. And it's CC by SA 2025, so if you want to just make your own like this, you can download all the files, the code and everything you need for free on the Element 14 community and just make your own. Or you can modify them and make it better or more suited to your needs. Maybe you want different batteries, different buttons, or a different screen. The choice is yours. Just go crazy with it and make sure to show me your creations. So, but now it's time to check out if this thing even works. Okay, let's do the demo. If you switch it on over here, it just boots up element 14, it just says element 14% 00 calculator by Maya makes. This should be maybe a bit longer, but it's ready within a second. So now we can basically enter our calculations. I ever wanted was 1 plus 1 was, 2, that makes sense. I can just go plus 5 and it's 7. So you can add with this like on the adding machine by just going next operation and the number, and it will just add to it. But there are some limitations. I can, and this is quite nice, I can just enter a new number. Oh no, I mistyped. I can just delete individual parts of that number and keep on calculating, which doesn't work with the other machine. So that's a more modern calculator feature. It also has, of course, a full clear. This should do the backlight and activate or deactivate it, but it doesn't. I've got the wrong kind of transistor in there. Maybe I even made an error in the schematic. Maybe you can find it and tell me what I did wrong. And this power switch here was supposed to do some sleep mode stuff. Yeah, basically, I figured just a switch. I just like switches and hard power offs. It's just the way I roll. Oh yeah, and you can do a very neat thing that shows you that this is truly an 8-bit machine. So how can I show you that I just utilized this 8-bit machine as an 8-bit machine? So it's truly an 8-bit calculator. 6535, no. It's 6535, no. It's 65535, I think. That's a 16-bit value times 65535 equals. Now we have this very, very long number. It's 42948362224.00. If I want to add 1 to it, I can't, because that's the biggest addressable number for this calculator. If you use some clever programming, you can get around that limitations. That's how 8-bit computers did their computing, by getting around limitations. Also, the floating point position is just 2 decimal places. So if I add like 12.5 plus 12.5, it will give me the right answer with 25. But if I have something like, let's say 1.256 plus 1.254, then it will just say 1.58, because it only can calculate to 2 decimal places. You also can get around that with clever programming by just shifting the decimal point. But I didn't do that because I think I don't really need those decimal places, and I really don't need those high numbers in my day-to-day life. But I also wanted to show you that this is why we moved from 8-bit to 16-bit to 32-bit to 64-bit machines. It's part of the reason. So if you are clever with programming, you can give this more capabilities. Download the code and give it a shot maybe. We have satisfied my need for a big honking desk calculator in a more updated form factor. So we now have an equally sturdy piece of tech that we made ourselves, that fully open sources all the things. And because I messed up the assembly a few times and had to remove buttons because I put them in the wrong way and I had to reprint them a few times, I even ripped apart buttons. So I can attest that this is very repairable, as all things should be. Let me know what you think on the Element 14 community, and I gotta go. There's another project waiting for me.